It doesn't take a second to catch a rat, to drop a cat, to blink an eye, to throw a pie. To drop a cat takes a quarter of a second. To catch a rat takes 1/10 of a second. To blink an eye takes 1/5 of a second. It takes a fraction of a second to throw a pie. To bump a tire, to strike a fire, to type a letter, to see things better. To see things better, this is the job of the high-speed camera. You've just seen pictures taken at a rate several hundred times faster than normal projection speed. You've seen fast action that was once lost in a blur of motion. Such pictures are possible because the camera transports the film in a smooth, continuous motion instead of stopping it for each frame. The taking lens places an image on the film just about the same as any camera. But the film passes the aperture so quickly, it would seem it could never catch and hold a sharp image. This roll of film, hundreds of seconds of projection time, can catch an event of 1 second or less. To see how a sharp image is formed, let's slow this action down. With the cover and aperture removed, you can see the prism which is between the lens and the film. The prism, turning as the film moves, sweeps the image with the continuous motion of the film. An aperture plate restricts the image to the desired frame area of the film. But let's see how this engineering analysis tool is put to work. In the research and development, in scientific investigation, in manufacturing. Aerospace programs are large users of high-speed cameras to study the performance of entire rocket vehicles. These cameras also study systems and tiny parts, any one of which could affect the entire project. How are rocket engines developed, tested, improved? At Hercules Powder Company near Salt Lake City, Utah, engineers are designing and developing solid fuel rocket motors for America's missile might. On this remote mountainside is a production line for packaged power. In the test cells, each firing is a one-time thing, with no chance to repeat. No test is run without the high-speed camera, for when there's fast action, these films slow the action, magnifying time to show the engineers what really happened. Subject for this test, a rocket motor with more than 30,000 pounds thrust. And in particular, red plugs which close the nozzle opening. This cameraman is nodding his head for a purpose. He is using a precision focusing technique for which the FASTAX camera is specially equipped. When he sees no image shift as he moves his head, he knows the image is focused sharply at the film plane. But these cameras take no special skills. Good cameramen master them in short order. Even this advanced model, which takes a 1,200-foot magazine and features precision speed regulation. The subject is ready for the test. And so are the high-speed cameras. We'll see it first as filmed by the normal camera in a night firing. What happens when the motor starts and the red plugs snap out? It's too fast for the eye or for the normal camera. In the FASTAX film, watch the plugs blow out. The action is stretched 100 times, clearly revealing the functioning of the engine start. But sometimes engineers want to see even more. They want to see inside a rocket engine. At North American Aviation's Rockedyne division, this is a glass wall liquid rocket engine. Doesn't look much like a rocket engine, you say. You're right. You're looking at steel framework holding the glass walls, which are the sides of a cutaway research engine. Now you're looking at the nozzle end of this slice of rocket engine. You can see the edges of two glass walls on each side. You can see the special plate to deliver the fuels. This cutaway engine gives the engineers a look inside the combustion chamber. But when you're dealing with fast action, there is no way to really see what is happening without the high-speed camera. Here at night again is the firing as it would seem to the naked eye. The run must be short to avoid overheating the glass. But how did the engine light off? What were the characteristics of the fuel mixing and burning in the combustion chamber? Let's view it by FASTAX at 8,000 frames per second. First, the action of the igniter. Then, as the fuels are delivered, the flame pattern spreads through the combustion chamber in a manner clearly visible. Each color is significant. The engineer can study a normal, stable flow. Then, by causing it to be unstable, he can study erratic burning, which could destroy a rocket engine. With new knowledge from this high-speed photography, he can improve the reliability and performance of his product. Even the color and pulsations of the light from the burnout are meaningful when slowed 300 times. High-speed cameras help engineers study a new kind of light, the light from a laser beam. Light with enough energy to heat and explode a balloon is being studied in the laboratories of Aerospace Corporation. The study of laser technology offers much promise. For the first time, it is possible to produce light which is very directional, coherent, and intense. The heart of this laser is a ruby rod, which is energized by strobe flash tubes. Light builds up in the rod and comes out in a brilliant pulse of concentrated light energy. Liquid nitrogen cools this apparatus since the heat generated is considerable. The laboratory studies are aimed at channeling this intense beam for applications, such as space tracking and communications. You will see a laser beam slowed 160 times by FASTAX, lasting 1/10,000th of a second, as it strikes a filter and heats it to destruction. This plastic block will receive a laser pulse with a temperature of about 14,000 degrees Fahrenheit. The impact of the light beam chips it just like an ice pick. The beam of light can be focused so sharply that it will drill a hole in the hard steel of a razor blade. Such laboratory studies are more than stunts. With the aid of high-speed photography, scientists are learning more about this new kind of light. At Cedars of Lebanon Hospital, Dr. Henry J. Rubin has built the FASTAX camera into the upper structure of an instrument for the study of the larynx and the vocal cords. The physician can observe through a viewfinder and by means of a mirror how the larynx functions as the person makes sounds as in speaking. He can see the vocal cords move apart for breathing and come together to make sounds. But to see the vibrations, here at about 100 cycles per second, he needs the high-speed camera at the 5,000 frame rate. So it's lights, camera, action. The vocal cords are slowed 200 times as the FASTAX camera brings new insight, new medical knowledge of the functioning of the human body. At Autonetics Division of North American Aviation, the Minuteman guidance system is in production. Even these tiny resistors must meet the highest standards of reliability, so the missile will be ready at all times. In many lead-bending machines, these costly elements are carefully prepared for assembly at a rate of several thousand per hour. But there must be no damage as the machines clamp and shear and bend the leads from the miniature resistors. Quality control engineers use the high-speed camera to be sure. At regular intervals, high-speed film such as this is reviewed by the Quality, Reliability, and Standards Department, and the machine is tagged acceptable when they see the proper action. These motions, which are completed in a few tenths of a second, are expanded and magnified in time to 30 seconds or more. But fast action is more than research and development, more than quality control. In manufacturing, such as at Munsingware, high-speed photography is a key to productivity. When you have row upon row of production machines, even a small increase in machine speed can make a big difference in production costs. But productivity without quality is waste. And if the high rate produces material with flaws, then perhaps the machine should not run so fast. But how do you know what is happening? How can you study such fast action? Can you afford this? Can you afford a reduced production rate? Not if you want to stay ahead of your competition. How can you see what's really happening? At this point, the needles are performing 350 knitting actions per second. The setup of the high-speed camera is simple. The knitting needles are poised and ready. How do they function at the desired speed? The photography sometimes takes only a second, literally a second. And the fast action, which is a meaningless blur to the eye and to the ordinary camera, turns into a meaningful picture when slowed several hundred times. It takes only simple equipment to study these FASTAX films. And here, slowed from a rate of 350 actions per second, is our knitting machine. The engineers can see the regular formation of a knitted loop every other pair of needles. But look, there's a missed loop. You can reverse these films and study the action over and over until you know just what happened. There is the gap in the knitting and a clue to the problem. An action too fast to see with the naked eye or with the ordinary camera has been slowed for us to study and examine, slowed for us to see and to understand, to improve the productivity. So long as you maintain a satisfactory product, even a small increase in machine rate can deliver a good return on your investment for high-speed photographic research. It takes a variety of cameras to meet many different requirements. Of the 30 FASTAX models, these are representative. Simple and low-priced is this 100-foot 16-millimeter model, which can operate from 150 to 8,000 frames per second. In 8-millimeter, these cameras can operate up to 18,000 frames per second. Some cameras have two taking lenses, as this larger 400-foot model. When fitted with a second lens, whatever the film capacity, a prism superimposes a trace on the film, so that an oscilloscope signal can be correlated with a corresponding mechanical event filmed by a principal lens. This magazine-type camera has a start-stop capability and superior resolution. It carries a 1,200-foot magazine for the observation of longer events. But perhaps its most important feature is the closed-loop servo speed control. The camera will accelerate the film to the desired frame rate and then maintain this rate on a flat speed curve for simple data reduction. FASTAX cameras are also available in 35 millimeters. They are all ruggedized and designed to operate in tough environments. In addition, there's a complete line of accessories, such as this combined power supply and programmer for controlling the power and for synchronizing the camera and the event. FASTAX cameras fill a variety of needs for various applications and budgets. The use of these cameras is limited principally by the ingenuity of the engineer with a problem to solve. Let's look at a few contrasts in motion. Perhaps your imagination will relate your own problems as they might be solved by FASTAX. Perhaps you have a machine tool with a high cutting speed. You'd like to get right in there and see every detail of this high-speed cutting action, slowed several hundred times by the camera. Or you're welding with a new type of rod and you need to see the effects of welding current variations. This action is photographed at 6,500 pictures per second. You're shelling kernels of fresh corn from the cob, and your camera stretches the action 75 times to see things better. Perhaps you're a doctor conducting research into artificial heart valves. Here, a doctor is using the FASTAX camera to help determine whether the valves are performing a complete open-shut cycle at an accelerated rate equivalent to a lifespan. But at ordinary camera rates, you can't tell whether the valves close. You can when FASTAX slows the action over 150 times. You're conducting crash research to make cars safer to drive and to ride in. When the action is slowed, you can see what really happens at the moment of impact and roll. Engineers can learn more about safety features they must build into the automobiles of today. With FASTAX, you'll see action you've never seen before. Whether you have to catch a rat, drop a cat, blink an eye, or throw a pie. Yes, FASTAX is truly a time microscope, magnifying time and space. Its application to your problem is limited only by your own imagination.